So Nikola Tesla spent his life imagining a world powered by clean, abundant, efficient energy. He believed that the future of humanity depended on our ability to harness energy without destroying the planet in the process. So over a century later, one of the most promising technologies working toward that vision is the fuel cell. I spent a significant part of my career studying, modeling, and writing about fuel cells. I've authored two textbooks on the subject. One is called Designing and Building Fuel Cells, and the other is called PEM Fuel Cell Modeling and Simulation using MATLAB. So in this video, I want to share what I know about, or basically the basics of this fascinating technology. And I want to explain it as from a perspective of basic science all the way to the level of an engineer. So that way there's something in this video that anyone could take away from it. So what is a fuel cell? So I'm going to start with a very simple explanation. It's a device that converts chemical energy to electrical energy. And the only byproducts are heat and water, actually. So there's no hazardous byproducts whatsoever. So we feed this fuel. There's two fuels that are fed to it, hydrogen and oxygen from the air. And then the outputs, it produces electricity, water, and heat. So at the most basic level, we have fuel in, electricity out, byproduct is water. So if this sounds very familiar to you, it's because it's identical to something you use on a daily basis, the battery. So the battery also produces electricity through an electrochemical reaction. But this is where there's one way fuel cells and batteries differ. And this matters a lot because it determines what applications they can be used for. So the battery is an electrochemical energy storage device. The chemical reactants produce the electrons, electricity, and they're all inside the battery itself. When the chemicals are consumed, the battery is no longer useful. It's dead. It won't create any more electrons. So you have to put energy back in to regenerate those reactants. So that's actually how a rechargeable battery works, is that the chemical reaction reverses itself in those battery types. So a fuel cell is an energy conversion device where the reactants, hydrogen and air, as long as they're fed to the fuel cell and supplied continuously, you'll keep getting electricity. So it doesn't run out the way a battery does, and it doesn't need to be recharged unless you think of just supplying more fuel as a way of recharging. So a battery is like a tank of water or a pot of water. It holds a fixed amount of energy, and when it's empty, it's empty. But a fuel cell is kind of like when you turn on your faucet and you're running the water into it and it's running back out. As long as you're continuously running that into the pot, it will provide electricity. So these two distinctions have a profound effect on the applications. So for long-range transportation, backup power, portable power, the ability to just provide more fuel rather than having to recharge is a significant advantage. So how does a fuel cell work? So let's look at the science behind it. So this is where it gets fascinating. So the most common type of fuel cell, and the one I'm going to focus on in this video, is called the polymer electrolyte membrane fuel cell, or it's for short PEMFC. This fuel cell is used in vehicles, portable power systems, and many other stationary applications. So there's three main components sandwiched together. There's an anode on one side, a cathode on the other side, and a membrane in between. This membrane is called a polymer electrolyte membrane in between the two electrodes. So this is what happens when a fuel cell operates. And I want you to try to follow this at a molecular level. So a hydrogen gas is fed continuously to the anode, which is the negative electrode. Then the hydrogen molecules contact the catalyst layer at the anode, which is usually platinum. And the catalyst actually splits the hydrogen molecules into protons and electrons, which is interesting. So they can't stay in this form in nature by itself. So it needs some help to redirect them. So the electrons kind of get siphoned out with an electrical wire and a load. So that provides the electricity. The protons actually flow through the polymer membrane to the cathode. So once the electrons get there, it actually combines with the oxygen from the air and produces the byproduct, which is water. So water, right, is H2O. It's just hydrogen and oxygen. So that membrane in between the electrodes is designed to conduct protons while blocking electrons. So this forces the electrons to go through an external circuit rather than taking the shortcut through the membrane like the hydrogens are. So at the cathode, right, the air arrives and there's a catalyst on this side as well that splits the oxygen ions. So hydrogen, oxygen, they combine together and form water. So the only byproducts of the process are water and heat. So what you have is hydrogen and oxygen in, electricity and water out. There's no combustion process, no carbon dioxide created, no pollution, only electrochemistry here. So this is why the fuel cell represents such a compelling vision of clean energy. The process is clean at the point of use. And so just like other renewable energies like wind and solar, the process is clean. So how do fuel cells compare with heat engines? So this is the technology that currently dominates energy conversion today, right? The heat engine. So when you burn gasoline in an internal combustion engine, you're running a heat engine. That heat engine converts chemical energy into electricity through a multi-step process. So the chemical energy, right, that's from our fuel, our gas. It's converted into thermal energy through combustion. The gas is literally combusted in these engines. And then that mechanical energy is converted into electrical energy by a generator. So in that process, there's 3 steps, multiple devices, moving parts. Of course, those wear over time, require maintenance. But here's the critical physics. Heat engines are limited by Carnot's law. Carnot's law says that the heat engine depends on the temperature difference between the hot side and the cold side of the engine. So no matter how well you design a heat engine, you cannot exceed the thermodynamic limit of any type one of these systems. You can't exceed the thermodynamic limit. So what this means is that the internal combustion engines operate at most the 25 to 40% efficiency. So most of the energy is actually lost as waste heat in this process. So fuel cells are not governed by Carnot's law. They convert chemical energy directly into electricity without going through heat as an intermediate step, although there is some heat generated during the chemical reactions in the fuel cell. But the efficiency ceiling in a fuel cell is much higher. Fuel cells operate at 50 to 60% efficiency. And then if you have a combined heat and power system, they can operate up to an 80% efficiency. So the fuel cell stack in itself has no moving parts. So it has no pistons, no crankshafts, no turbines. This means that fuel cells are reliable, they're quiet, and they require less maintenance. So this is one of the reasons why fuel cells have been used in space missions. The reliability of a system with no moving parts is really valuable in an environment where maintenance is difficult. So for the engineers, here's the components in depth. In the fuel cell stack, I think it's fascinating for everyone though. So if you're not an engineer, you could still learn how this works. So one of the interesting parts of the fuel cell is the polymer electrolyte membrane. This is the heart of the PEM fuel cell, and it conducts protons from the anode to the cathode while blocking electrons. And it also prevents fuel and oxygen gases from mixing in there. So the hydrogen is on one side of the fuel cell, the oxygen is on the other side. So this electrolyte membrane is actually a Teflon-based polymer that was produced originally by DuPont. It's known under the name Nafion, and one of the most commonly used variants is Nafion 117. There's also Nafion 112, 115. Those represent different thicknesses of the membrane, and it depends on your fuel cell design. So what makes Nafion remarkable is its chemical structure. There's a polymer backbone that's made of polytetrafluoroethylene, which is Teflon. And so it gives it extremely good chemical and thermal stability. So it's resistant to strong acids and bases, oxidizing agents, and it's relatively resistant to high temperatures, up to about 125 degrees Celsius. So attached to this Teflon backbone is they're actually sulfonic acid groups, which are negatively charged groups that actually conduct the protons. Basically, the protons are jumping from one site to another throughout this membrane, and then they emerge on the cathode side. So you could think of it kind of like the proton is like a monkey swinging through the trees. That's kind of how it's moving through this polymer membrane. So the one critical constraint of the using this membrane is that it has to remain hydrated in order to conduct protons effectively. So in order for it to transport those protons, it has to be hydrated. It has to be wet. So because of this, this limits the operating temperature of fuel cells to below the boiling point of water, which is typically below 80 degrees Celsius. And so water management in these fuel cell systems are extremely challenging because you have to have the right amount of hydration in order for the protons to conduct effectively. And, then you can generate more electricity at a faster rate and so forth. So I spent some time on this challenge in my own research and in my books. Water management is genuinely one of the most complex aspects of fuel cell engineering. Too little water, the membrane dries out. You don't have good proton conduction. Too much water, the electrodes flood, and then it limits the access to the catalysts. So there's the two electrodes, right? The anode and cathode, just like in batteries. These are made of a porous mixture of carbon-supported platinum, and they're put on a carbon-based backing layer. So platinum has been the catalyst of choice for PM fuel cells for decades. They do mix in other types of catalysts sometimes, but this has pretty much been the standard. So it works both for the hydrogen oxidation reaction and the oxygen reduction reaction at each one of at the anode and cathode. But this has presented a problem for decades for fuel cells because one, for cost, and two, for commercial viability, because platinum is expensive. So you have to have a certain amount of platinum loading in order for the chemical reaction to be completed effectively. And so this has been one of the most active areas of fuel cell research for quite a long time now. So the electrodes are porous for a critical reason. There's a three-phase interface at these electrodes. This is where the reactant gas comes together with the catalyst and the membrane. So they all kind of meet at all those junctions inside the fuel cell. So all three must be present at each location at the same time in order for the chemical reaction to work properly. So you want to maximize basically the number of these three-phase interface sites. So the structure inside of there is usually a porous three-dimensional structure rather than a flat surface. And so most fuel cells use very thin membranes, and then also electrodes that sometimes are manufactured directly onto the membrane surface. So that way there's a maximum amount of contact between the electrode and the membrane. So one of the other critical components are the gas diffusion backings. So between the electrodes and the flow field plates, these are layers of porous electrically conductive material. These usually consist of carbon cloth or carbon paper. So these backings serve multiple functions simultaneously. They distribute the reactant gases evenly across the surface, the electrode surface. They provide electrical connection because they can conduct electrons also. And they help to manage the water. So they help to draw the product water away from the cathode to prevent flooding. But as I mentioned earlier, you do want a certain amount of water in the membrane itself. So it's a fine balance there. So the design of the gas diffusion backings involve a careful trade-off between porosity, electrical conductivity, and hydrophobicity. So if it's too porous, there won't be good electrical conductivity. If it's too dense, the gas distribution suffers. So another critical component in fuel cells are the flow field plates. So these are kind of the backbone of the fuel cell. They separate each cell and connect them electrically in series. and they distribute the gases to the electrodes through the channels on their surfaces. So the design of the flow channels affects the fuel cell performance, just like these other components that I've just described. So there's two primary flow field designs used in PEM fuel cells. They're the serpentine design and the parallel flow field design. In the serpentine design, there's just one channel, like it's a single channel that what kind of winds back and forth across the plate. And this design ensures that there's no blockage and accumulated water inside a channel. So the reactant sweeps through the path continuously. The disadvantage is that the reactant is depleted along the length of the channel, so the reaction rate sometimes is not consistent across the entire electrode. So in the parallel plate design, there's multiple channels that kind of run in parallel, kind of side by side from the inlet to the outlet. This sometimes provides a more uniform reactant distribution, and sometimes it also lowers the pressure drop. So the disadvantage is that the blockage in one channel creates a dead zone downstream, um, and that as the flow redistributes to other channels. So in practice, the serpentine design is usually the preferred design for most fuel cells because it has superior water drainage characteristics, which is critical because of those water management challenges that I mentioned earlier in the video. So most flow field plates are made from graphite, sometimes pure graphite, sometimes resin impregnated graphite. This graphite's highly conductive, it's chemically inert, and it's also corrosion resistant. The only downside is that it's not easy to machine, so it's a little bit more costly. So that's also a barrier to cost reduction for fuel cell systems. So fuel cell stacks and their applications. So a single fuel cell produces a voltage of about 0.6 to 0.8 volts under standard operating conditions. So this is not enough to power most devices. So in order to obtain the power levels needed to power things, fuel cells are connected in series to form a fuel cell stack. So the voltage of the stack actually equals the voltage of a single cell multiplied by the number of cells, and the current, therefore the power, is determined actually by the electrode area of each of the fuel cells. So voltage times the current will equal the total power. And by choosing the number of cells and the electrode area, engineers can design fuel cell stacks for basically any power requirement. You could design a small stack to produce a few watts for a portable device to a megawatt power plant. So scalability is one of the most powerful characteristics of fuel cell technology, and it's something that heat engines actually can't match. So the efficiency of a heat engine drops when you scale it down in size. The efficiency of a fuel cell stack is dependent on the system size. So a small fuel cell stack can be just as efficient as a large one. So this makes fuel cells uniquely suited for a whole range of applications. So from portable electronics, vehicles, backup power systems, and large stationary power plants. The applications have historically been most developed are for transportation, fuel cell vehicles, which are now finally commercially available from several manufacturers, and stationary power, where fuel cells provide highly reliable and efficient electricity generation for buildings and facilities. So Nikola Tesla imagined a world where energy was clean, efficient, and available to everyone. And he worked toward that vision with extraordinary dedication throughout his whole life. So fuel cells are not the only technology that realizes this vision, but they represent one of the most scientifically elegant and promising pathways towards it. So direct conversion of chemical energy to electrical energy, there's no combustion, no carbon dioxide, and water as the only byproduct. So the engineering challenges have been real in terms of durability, cost, hydrogen production, storage, water management. These are not trivial problems, but they are engineering problems, so they're solvable. And the researchers and engineers around the world have been working on these for quite a while now. So I've spent a significant portion of my career working on these problems and writing about them. So if you want to go deeper into modeling, simulation, electrochemistry, I have 2 books published on this. Designing and Building Fuel Cells, originally published by McGraw-Hill, and PEM Modeling and Simulation using MATLAB by Elsevier Science, both available on Amazon. So the links are in the description. So subscribe to this channel for more on the science and engineering of energy, and from the fundamentals to the frontiers of energy. My name is Dr. Colleen Spiegel, and I'll see you in the next video.